Oh, stop! Oh my God.
I did
Okay. Last time we were talking about, on Friday we started talking about relative motion. But not all everyone got a chance to practice that, so let's remind ourselves of what's going on. Right. So yeah, let's just get used to the notation. Let's look at this problem. We don't need to vote, just read through the problem. And yeah. So we have observing A standing on the side of the road, observing B moving with a velocity of -15 meters per second with respect to A. Both observing a third person P driving on the road in positive x direction. A measures the speed of P as a speed of 35 meters per second. What speed does B measure? So first, let's sort of refamiliarize ourselves with the notation. So, for example, this quantity here, I think of it as, or I read it as velocity of P with respect to P, right? Or velocity of P as seen by P. And what I can do is I can express that as the sum of two other velocities. And the way I remember the order of the subscripts here is I think, okay, P is on top over here, so it should be the first one here. B is at the bottom over here, so it's going to be the last one here. And then who's my other observer? A. So that is going to fill in the two middle slots so that they can sort of cancel out. All right, let me try and apply it to this problem. What information do I have? I have the velocity of B with respect to A. Right? It says observer B is moving with a velocity of -15 meters per second I hat. I also have the velocity of, what other velocity do I have? Hold it up.
35.
No, I mean, whose velocity? P with respect to, yes. P with respect to A, yes. So 35 meters per second, and we're told that P is moving in the positive I hat direction, so that I can put it as positive I hat there. All right, and so I'm going to try and put them in here. So velocity of P with respect to A, sure, that I have already, 35 meters per second I hat. But this asks me for velocity of A with respect to B. But what I have is B with respect to A. How can I turn that into, yes, later? It will just be in the opposite direction, that's right. So the velocity of A with respect to B, I can flip the order of these subscripts at the cost of a minus sign. So this becomes positive 15 meters per second I hat. So I can put that in here, plus 15 meters per second I hat, then I can add them, and so I get velocity of P with respect to B is 50 meters per second I hat. So sort of the two important things to remember are, one is that you can split any relative velocity into the sum of two other relative velocities, and the other is that you can reverse the order of these subscripts at the cost of the minus. Questions? Feel free to ask questions at any point. Let's try. Anyone need more time? Bit more time, okay. People need more time or are you ready? All right, let's take a quick vote on what people think. Okay, all right, pretty evenly split actually. All right, so let's go through it. Just so again, I can show you how we set up the all right, so I'll put the relevant information on the board, the whiteboard, and then I'll screen up so I can use the blackboard. All right, so what information do we have? Well, the first thing I should do in these sort of relative velocity problems is just as a matter of bookkeeping, think of letters to use for my various observers and objects. So I have a river. Okay, so I'll use R for river. I have the observer on the river bank, so I'll use G for ground. I'm not using R because we've already used R for river. I'm not using B because I'm going to use B for boat. Yes. Okay. So then let me summarize the information that we're given. A particular river flows at a speed of 6 meters per second. So how would I write that? That is the velocity of river with respect to ground. Yes. Well, right now that's just a speed, right? Velocity or the speed of the river with respect to the ground is 6 meters per second. I have 6 meters per second, and then what I can do is I can choose my coordinate axes so that the river is flowing in the positive I hat direction. So I'll make a note here. River flows in plus x direction. So then I can make this a velocity and make that 6 meters per second I hat. All right. And then what's the next thing? We say a speedboat is moving, maximum throttle, moves straight downstream. Observe on the riverbank mentions its speed is 17 meters per second. So how should I record that? That is the velocity of, yeah, just call it out. The boat with respect to the ground is 17 meters per second, and that is also positive I hat because it's moving downstream. All right, so starting with this, before we go on to the rest of the problem, we have these two relative velocities. What velocity can I find from these? The velocity of the boat with respect to the river, yes. So, yeah, let me put that here. And this is part one when the boat is moving downstream. And so I can say, okay, the velocity of the boat with respect to the river, I know it's going to be the sum of two other relative velocities. So just call out how I should fill out the subscripts. So this one should be D, right, over G, and then G over R. Yes. Yes. Is that
Yes.
okay? Sorry. Okay, so yeah, so we have that. So then let's plug in what we know. Both with respect to the ground, we have is 17 meters per second I hat. And then this one asks for velocity of the ground with respect to the river. What should I put? -6 meters per second I hat. Right, because this was river with respect to the ground. What I want is ground with respect to the river. Okay. Remember, it's sort of like if you're in a train, you think that you are stationary and the ground is moving behind. Yeah, the other way. Okay, so then this gives us 11 meters per second I hat. This is the velocity of the boat with respect to the river. And this is when the boat is moving downstream. Questions? Amit, yeah.
Yeah, I mean, I pretty much put the same answer, but I was using.
We haven't finished the whole question. I'll say that.
Okay.
Yeah.
Then
We'll wait until, okay, all right. Other questions so far? Okay, so this is the boat with respect to the river when the boat is moving downstream. So now we'll continue on to part 2 of the question. It said now the boat turns and goes upstream. Okay. And so the velocity of the river with respect to the ground, that hasn't changed. That is still 6 meters per second I hat. But now the boat is going upstream. Its speed with respect to the water stays the same, but now it is moving upstream. So we can say that the velocity of the boat with respect to the river is now negative 11 meters per second I hat. Question? Okay. All right, and so then again, we want to find the remaining relative velocity. And the question is asking for the velocity of the boat with respect to the ground. So we're going to write that as the sum of two relative velocities. So again, just call them out. This should be B over R over G. Right, so B is the first one, so it comes here. G is the bottom one, so it comes here, the last space, and the remaining observer R fills the remaining two spaces. Then we can plug in our information. Boat with respect to the river is negative 11 meters per second I hat. River with respect to the ground, 6 meters per second I hat. And so what we see is that the observer on the ground will see the boat moving at negative 5 meters per second I hat. The minus sign simply tells us that it's moving upstream, right? So it is moving faster than the river is flowing downstream. So it does make its way upstream, but at a slower speed. Yes.
yeah, I think my question is why can't the observer be a reference point itself? Like why is it a reference like the board to observe observers ground? Because I mean when I was trying to put the notation, I was using the observer as one of the reference points.
I see. Yes, no. So your observer is the same thing as what I'm calling ground. All right. So yes, you could definitely, instead of ground, you could put O for observer. That's perfectly fine. Yeah. Other question? But yeah, if anything pops to mind, feel free to raise your hand and ask a question. All right, let's try something a little bit more conceptual. Let's try this question. All right, show me what you think. Okay, all right, interesting. So I'll actually go straight into discussing this one because the solution actually does require a bit of information that we haven't really talked about in this course. So most of you voted for P, but the answer is in fact Alice. Yeah. Okay, so why? Why is it easier for Alice to take off? So the bit of information that you didn't have that you needed is that for lift, right? For on a plane, right? The way that a plane gets lift is from the air flowing over the wing. And so the faster the air flows over the wing, the more lift it will generate. And so for Alice, because she's heading into the wind, right? The speed of the air over her wing is greater, and so it generates more lift, and so she gets off the ground much easier. Now, once they are in the air, right, then Bob will be moving faster, right, because he has what we call a tailwind. If you've ever taken an international flight and heard the pilots say, "Oh, we're actually landing early because of favorable wind conditions," that's because you had a tailwind. So that is, once you're at cruising altitude, you will move faster if the wind is pushing you along from behind, okay? But getting off the ground, you need lift for that. And so yeah, so Alice will have an easier time getting off the ground, but assuming Bob does make it, he will get there faster. Yeah. Okay. Right. So then, let's see. Oh yeah, we'll do a quick demo. So we've been talking about sort of one-dimensional relative velocity questions, but it doesn't have to be that way. Sometimes the velocities you're adding are in different directions. So here you can see a little toy car, battery powered, moves in a straight line, right? So we can talk about the velocity of the car with respect to the paper that is moving on, but I could move the paper. Of course, I could do it as a one-dimensional problem. So I could pull this. If I pull it at exactly the right speed, then the car basically stays in the same position relative to the classroom, right? Basically, my pulling the paper has neutralized the motion of the car with respect to the paper. Mythbusters actually had a really cool stunt where they fired a cannonball from a moving truck. And so they first measured how fast the cannonball would be coming out of the cannon. And then they drove the truck at that exact right speed. And so when they viewed it from the side, the cannonball just came out of the cannon and just dropped straight down because it was, yeah, it's really cool. You should watch it on YouTube. So yeah, but I could also pull the paper sideways. And so then you see that even though the motion of the car is, say, in the plus X direction, and the motion of the paper is, the motion of the car with respect to the paper is in the plus X direction, and the motion of the paper is, say, in the plus Y direction, the combined motion that the car has with respect to the classroom is in some diagonal direction, depending upon the components. So we're gonna look at a problem similar to that. So go ahead and yes, go ahead and read through this problem. And then I'll sort of take you through it. So we have this. It's flying, but there's wind blowing. So I'm going to summarize the information that we have over here on the whiteboard, and then I'll put the screen up and use the blackboard. So first I need to figure out letters for my various objects and observers. So I guess I'll do G for ground instead of goose, because what shall I use for goose? B for bird. And what else do I need? A for air. Right. Okay, and so we're given some information. One such bird is flying at 100 kilometers per hour. How should I write that? B over A, yes, because we're told it's 100 kilometers per hour relative to the air. Okay, and yeah, so it's 100 kilometers per hour, but this is just a speed right now because we don't have the direction. In fact, that's what the first question is about, is what direction should the bird point? Okay, and then we have the wind. How should I write that velocity? We've been getting a lot of answers. Oh, Zoe, actually, yes.
The air to the ground.
Air with respect to the ground, yes. All right, but I haven't set up my axes yet, so let me do that. Then I can put it in like I have J hat form. So as usual, call this north, that one east, make it north positive y, east positive x. So this would be west, this would be south. So with that in mind, I can say that the velocity of the air with respect to the ground, we're told that it's 40 kilometers per hour and it's blowing from west to east. So 40 kilometers per hour, I have. Now it's a vector. Okay. Let me turn off the camera. Yeah, I think it did that by itself almost. Yeah, it's off. Okay. All right, so velocity of the air with respect to the ground. And the first question I asked is, at what relative angle to the north-south direction should this bird head so that it will be traveling directly southward relative to the ground? All right. I'm going to put the screen up and turn off the projector for that so I can use the report. Any questions or any information you need from here? No? Okay. So. All right, so what do we have? We have the velocity of the air with respect to the ground. And what we want, I should have put that on the whiteboard here, just jot it down. What we want to achieve is that the velocity of the bird with respect to the ground should be in which direction? South, yes, due south, so that would be negative j hat. So in negative j hat direction due south. Okay. So air with respect to the ground, we have that is moving like that. And what we want is that the velocity of the bird with respect to the ground should be like that. But we don't know its magnitude, we just know its direction. Okay, so we know that if we have two relative velocities, we could probably figure out a third one. Third combo would be bird with respect to the air. All right, what would that be? Call it out. B, G, A. All right. So bird with respect to the ground, okay, we have that direction. Ground with respect to the air, what do? Move it the other way, flip it. So I know that the bird with respect to the ground is pointing in this direction. I don't know how long it is, but I know that's the direction. And then ground with respect to the air, I know it is going to be that direction. And so the sum of these two vectors should give me bird with respect to the air. All right. And we actually have some magnitude information. What magnitudes do we know? G over A we know is how much? It's negative direction and magnitude is 40, that's right, 40 kilometers per hour. Sorry, yeah, just plus 40 kilometers per hour. What other magnitude do we know? B over A, yes, the bird we know is traveling at 100 kilometers per hour with respect to questions. Yes.
Don't we technically know B over G because we have B over G?
Remember that these are vectors. So you can't just add 100 minus 40. Because those are just magnitudes, right? You want to put this in vector form. If you put it in vector form, then you can add. Right? But the problem is we don't know the direction of this just yet. Other questions? Okay. But what we're trying to find is precisely this angle theta, right? They asked us for the angle with respect to the north-south direction that the bird should head. So questions on how I would find theta?
Pythagorean theorem.
So again?
Pythagorean theorem.
I could do Pythagorean theorem, that's right, because I have the hypotenuse and I know one of the sides, so I could use square. I can also do trig, right? Which trig function would I use? Sine, that's right, because I have the opposite side over here. I know that this side is the same as this side, which is 40 kilometers per hour. And so I can say that theta is inverse sine of 40 over 100. Can someone calculate what that is? .6, is that degrees? All right, thank you. All right, so that gives us the heading of the bird. The bird should point itself at 23.6 degrees west of south, right? So direction is 23.6 degrees west of south. Question?
With the, I'm just like wondering what like velocity of the ground with respect to the air when it's not.
Oh, it is, well, the negative, I was just putting the magnitude here, right? And so you're correct, the direction is in the opposite direction of this. So if I'm writing it as a vector, I would write velocity of the ground with respect to the air is negative 40 kilometers per hour I. Yes,
Does it have to be west of south? Could it be like east of north? Is it sort of like the same?
well.
Because they don't specify, like the question doesn't specify like. What direction?
No, the direction that the bird is heading south.
Oh, okay, sorry.
Yeah,
that's-
All right, so. So yeah, so we have velocity of ground with respect to air, we figured out this angle. And so then now, so yeah, so I have that direction, and that is the direction of the velocity of the bird with respect to the air. So I can either put it in component form, or I can say it is 100 kilometers per hour at 23.6 degrees west of south. Right, because this is south, and then west of south will turn it that way. All right. Now, the other question asked, how long would it take the bird to cover 500 kilometers on the ground while flying, as in like, you know what I mean? So for that, I need this speed. So how would I go about finding that?
Either trig or Pythagorean.
Yep, again, trig or Pythagorean. So if I was doing trig, I could say, well, this is a nice right triangle here. And so I can say that the velocity or the speed of the bird with respect to the ground would be 100 kilometers per hour. And then cosine 23.6 degrees. Can someone just calculate that?
$91.7.
91.7, thank you. All right, 91.7 kilometers per hour. And so then the time, because it's moving at a constant speed, I can say the time is just distance over speed. And so if the distance to be covered on the ground is 500 kilometers, it can be 500 divided by 91.7 kilometers per hour equals 5.5 hours. All right. Questions? Oh, yes.
Why actually, I mean, why I pick one use management site for the rotation of the dagger and not the total?
Oh, no, you absolutely could. I mean, no, you absolutely could. It's just because for this one, I didn't know the direction at the time I wrote this, so I just wanted to put that there as a reminder of the magnitude. Sorry. Yeah. Yeah, if you, okay, since people seem disturbed by that, I can just remove the arrows there, and then that makes it an ambiguous there. Yes.
I just wonder why we chose diagram.
Because I wanted to add up these two vectors, right? Or equivalently, yes, I could do this one minus this one, yeah. I just didn't want there to be any confusion, so it is. But I do want to point out that, so this time it happened to form a right triangle. That will not always happen, okay? This is a common mistake, is that you assume that the three velocities form a right triangle. No, they will form a triangle, but most of the time it will not be a right triangle. In this case, because one of the directions was due south and the other direction was like due east or west, it happened to form a right triangle. But in general, like supposing the wind was blowing, like if the bird was trying to head this way, but the wind was blowing at this angle, then you would have to add that vector. And so you'd end up with like a different triangle, right? where this would be your triangle, which would no longer be a right triangle. But as long as you had enough direction and magnitude information, you would be able to figure out the components and the relevant angles. And you will see a problem like that in your homework. So one thing that might be weird is you might say, well, wait, so that means the bird is pointing in this direction, but it's moving like this with respect to the ground? Like it's moving in the direction it's not pointing? How does that happen? It actually happens quite a lot, even with planes. So let's take a look at some planes. Landing in crosswinds. So what you will see is the direction the plane is moving is different from the direction of the plane. This first one, it's a bit hard to tell until it reaches the ground. Then you realize, oh yeah, it's not actually moving forward as such. Not that much, at least. The next one would be much clearer. It's definitely drifting sideways. Because the wind, its overall motion is in a different direction, at least until it touches the ground. After that, because of the friction in the ground, it can. Yeah, that's a really good stuff. Sidewalk. All right, so yeah, you can you need to correct for the influence of the wind, so you will need to point yourself in a different direction from the direction that you're actually moving. Okay, any last questions? Right, you'll get some more practice with this on the homework and in the Friday problem set. But if there aren't questions, let us move on to finally get Newton's laws. All right, so let's start with this question. Oh. Erase these. Anyone get more time? With more time. All right, tell me what you think. Mostly for E is correct, yes. So the trick to the question is when the question says like, oh, you're on an ice rink, or you're on the ice, then what that's code for is there's no friction. Okay, and so there's no friction here, and what we know is that if you want to move at a constant velocity, you don't need any force. Right? That is the natural state of an object, is that it will continue to move at a constant velocity unless it is acted on by some force. So in this case, the force required is 0. All right, so that brings us right away, in a sense, to Newton's first law. So let me write that down. New piece of chart. So, Newton's laws. First law. Many different ways of stating it, but I'm just gonna paraphrase a little bit. So. Actually, let me rephrase it slightly. Sorry, I'm just going to rephrase that slightly. All right. All right, there's a lot of words and we need to define some stuff. So in an inertial reference frame, if there is no force acting on an object, then a stationary object remains at rest and an object in motion continues with a constant velocity. So when we see this definition, what's one of the first questions that comes up? What's an inertial reference frame? Yes, so let's break that down into two parts. First of all, what is a reference frame? Suggestions? Yeah.
Perspective.
It's like perspective, yeah. To make it a bit more mathematical, it's you have an observer, right, whose perspective it is, and then they set up axes. Okay? They set up, okay, this is my positive x direction, my positive y direction, positive z, and also like when is t equal to 0 for me, they like set up a time axis as well. But that is what a reference frame is a set of coordinate axes for the positions and time. And then with respect to that, they can make measurements. All right. So then the question becomes, what is an inertial reference frame? And this is actually what the first law is all about. It is defining an inertial reference frame. What this is basically a test. And if your object passes this test, then you know that you are in an inertial reference frame. That's what it's about. Okay, so the idea is that you're in some reference frame, you've set up your axes, and you take an object, and you say, okay, there are no forces acting on this object, and you observe it. If it's at rest, does it remain at rest? If it's in motion, does it continue with a constant velocity? Then in that case, you are in an inertial reference frame. If it doesn't do that, right? If its motion changes, then there are two possibilities. One is that there is a force that you haven't eliminated yet, right? So there is some force acting on the object, or you are in a non-inertial reference. That's a little weird. Give it a moment to sink in. Questions? Yes.
Like, are we for the most part non-inertial reference?
Yes, good question. Yes, technically, the surface of the Earth is not an inertial reference frame. However, the forces involved are small enough that you can like account for them, and we will, for the most part, treat the surface of the Earth as an inertial reference frame. Right, so it's to an approximation, we can treat it like an inertial reference frame. But you're correct. Technically, the surface of the Earth, yeah, it's a non-inertial reference. Let me give an example. Supposing you are in a completely closed box and you don't know if you're on Earth or on the Moon or in space or wherever, it's completely closed. And you take an object, right? You take an object and you let it go. And what you see is that it just floats there in front of you. Okay. So then it would be a decent guess that, okay, there are no forces acting on the object. It was stationary, it was remaining stationary. So you are probably in an inertial reference frame. If, on the other hand, when you let it go, it falls, there are two possibilities. One is that there is a force acting on the object that you haven't removed. Right? So maybe your room is on Earth and the force of gravity is acting on the object. That's what caused it to fall. Or maybe you are actually in a rocket, right, in space, and what's looking like the chalk falling is actually more the fact that like both you and the chalk are moving up, but because you're accelerating, the chalk is not moving up as fast as you are moving up. And so the chalk appears to just drop to the floor. Okay. In that example, you are in a non-inertial reference frame, right? Because you are accelerating, and once you let go of the object, then it can't accelerate as fast as you are, and so it looks, its motion changes. If you were in a rocket ship that was moving at a constant velocity, then like you're holding it and you let go, then it still has that constant velocity and you would both be moving up. And so from your perspective, it would still look like it's floating. So we see this connection between inertial and acceleration that, oh, if there is no acceleration, then you're probably in an inertial reference frame, right? But this is really the test that this sets up, is like, can you pass this test? Can an object that you have pass this test? Then you are in an inertial reference frame. Once you have your first inertial reference frame, you can create other ones. Like if you have another observer whose only difference from you is they are just like 20 meters to the left, right? But they move exactly as you do. They're stationary with respect to you. Then if you are inertial, they are also inertial, right? But if they are accelerating with respect to you, then if you're inertial, then they will be non-inertial. Or if they're rotating actively, if they're spinning with respect to you, then they will be non-inertial. Yes.
If the box is like falling with you
Mhm.
and you drop it, so it looks like it's still floating because you're both like going with gravity, that would not be inertial. So,
You've hit upon a very deep question. So we won't go into detail on that, but basically Einstein asked that same question, and so when you go beyond Newtonian mechanics, special relativity, and then beyond that to general relativity, what we say, we change the definition of inertial reference frames to basically something that is falling freely under gravity. And so that, according to Einstein, that would actually be an inertial reference frame. But that's because gravity is a special force, and that's, yeah, that's a... Okay, we've reached the end of the time. I'll end with a short demo, and I'll save the fancier one for next time. So we said if there is a force acting, it will change the motion of the object. But if the force acts for only a very short amount of time, then it doesn't have enough time to have an effect on the object. So this is what we talk about when we say that, oh, a massive object has inertia, is you need a force acting on it for some time for it to change its motion. So here, this rod, this metal rod is stationary, And so if I'm quick enough in pulling this paper, the force will be small enough that it doesn't affect the state of the rod. So. All right, and so the rod. Alright, you'll see a fancier version of this next time on the alright. Oh, yeah.
Study for a little while.
Okay, well then, but I need to submit an excuse form.
Okay. See me put on rings.
Well, no, I mean, I don't need like a.
I was gonna-
Just like fill out the excuse form.
We are in the same class.
Sorry?
Are in the same, because, so I'm just, like, I thought you were, yeah. Like earlier in the paper.
Which class?
And laughing and like getting a little stressed out about all my other stuff, so I was wondering.
What you
Like
guys do?
how important the lab is to the class. As in like if I missed a drop in the lab, that would impede my understanding of the class.
Not significant, no.
Okay.
If it is stressing you out, yeah, feel free
Okay,
to-
so yeah, cause I just kind of, yeah, okay, and it would.
Right, yeah.
Football game? Is there a chance that game?
I saw guys doing that.
Yeah, probably I was just one of them. Got a lot of.
Yeah, you could appeal after the.
Try.
Because you have your foot, you still have your foot.
Yeah.
And so
Six, seven.
more time to sort of get into the enough force. I'd say talk to your,
And I
like, right, exactly.
No,
So
not
talk to
all.
your advisor about that, but yeah, I feel okay with that.
Okay, cause yeah, just I was looking at my schedule and I'm realizing that it's becoming too much, and like if the lab is something that's like bigger, I'm saying
No, it is independent.
Thank you.
Like within 5
all
minutes.
that.
So literally, they can add in.
Have a nice day.
Oh my god.
Which of which I've looked at and like.
Was this fast?
Yeah.
Okay.
My Saturday was quite productive until the football game. It's quite productive.
In what's class?
You like doing work and stuff, studying, and then Sunday morning,
Wait.
I was fucked.
Okay. Right, okay. So yes, that's a good question about terminology. So linear acceleration. People misuse this sometimes. Linear acceleration is the same thing as total acceleration. All right. And then this divides into the sum of two things, right? It divides into tangential plus centripetal acceleration. Oh, this is homework 3 submission. Okay.
Thank you.
Okay.
And yes, in this problem, you can assume that there's no tangential acceleration because it's a constant speed.
Okay,
So yeah, so total acceleration or the linear acceleration is just the centripetal acceleration,
okay. Yeah, cause like the velocity is constant.
or the speed is.
Or the speed, right, the speed direction changes.
Yes.
Okay, I think that makes sense then. So like, you can just use like the total speed, they could be as like the, or total acceleration as like the centrifugal acceleration, use like the AC is equal to B squared over R.
V squared of R or omega squared R, depending upon what information you have.
Okay, thank you. Have a good day.
You too. Oh, question. Did we decide anything about like homework 1?
Oh, I think you said like if I have time to do it, but I probably can like submit it, like I can do that.
Okay.
Yeah,
Alright.
I'll do that this week. Alright, thank you.
Hello. Did somebody find a white coffee cup in the front row?
About that, no, sorry.
What would I ask?
No.
Just one, just one.
No.
There's someone else's one. Why do we have them here?
I just think that.
Yeah. I read you have coffee cup from the
It's part of a demo, you'll see it on Wednesday.
Worried. I'm just gonna. Oh
So
my
can I go
God.
with them to turn it on Wednesday?
It's not my property, I can't give it to you.
Yeah, I thought somebody just finished breakfast. I know, I thought it was crazy.
Let me go and see.
Lock in.
Alright. I will need the tablecloth back, I didn't get around to that.
No problem. For both classes, for one class?
For both classes.
Okay, good. Yeah, just a question of, do I remove it if you wanted more
Right,
space?
right.
Yeah, no problem at all.
But yeah, the rod is done, the cart is done.
How did it go? Is it project well, both classes?
Well, I know you had put it at an angle first,
Mm,
but then when I projected it was sort of at a weird skewed angle, and so I turned it, but then when I turned it, there was not as much space to play with, but it was enough for the purposes that,
okay,
so it was fine.
yeah, I was debating, is it better to have it straight and a smaller field of view, or a little bit angled with a wider field of view, and.
I could sort of feel that they were like, could you straighten it, and like, yeah.
Makes sense. Yeah, that's really only something you can decide with feedback.
Exactly, yeah.
Sounds good. Correct. Right, I remember. Wonder if I can ask you a favor. In a little while, your students will be doing the coffee filter drop. I would like to have copies. All of the data that they take, all the movies. I am making no promises. Please understand, there are absolutely no promises being made here, but I'm trying to get enough machine learning under my belt